This is the video key for the Unit 9 practice exam. This first set of questions is all about mole conversions, so you have to keep in mind that flow chart that we had for the different ways that you convert between the different variables in this unit. Sometimes they're one-step conversions, sometimes they're two-step conversions, so it's important that you identify which we're dealing with. Question number 1 asks you, if you have 35.2 liters of helium gas, or hydrogen gas, how many moles do you have? So for this one, we are going from liters, which is volume, to moles. Volume to moles is a one-step conversion, so we just need to use the conversion factor going from volume to moles, which is 22.4 liters in 1 mole. So we start with 35.2 liters of H2. Then we want to convert from liters of H2 to moles of H2. And as I said, the conversion factor here is 22.4 liters in 1 mole. There are 3 sig figs in 35.2, and there's 3 sig figs in 22.4, so our answer should have 3 sig figs. You get 1.57 moles of H2. The second one, it says how many molecules are in 360.2 grams of phosphorus triiodide. So on this one, we are going from grams to molecules. That's mass to particles. There's not a one-step conversion process for that. You have to go through moles in the middle, so this one is a two-step conversion. We have to go from grams to moles, and then from moles to molecules. And then we have to use the 2 appropriate conversion factors there. One conversion factor that we're going to have to use is the molar mass, going from grams to moles. And so I'm going to go ahead and find that now for Pi3. That's phosphorus triiodide. So phosphorus has a mass of 30.97, and there are 3 iodines, and each iodine has a mass of 126.90. All right, and if you add all of those up, you should get 411.67. And that's grams per mole. So we start here with the number that's given, 360.2 grams of Pi3. We have to go from grams of Pi3 to moles of Pi3. And then we have to go from moles of Pi3 to molecules of Pi3. Conversion factor going from grams to moles is the molar mass. So this is where that 411.67 comes. All right, and that's grams in 1 mole. Then we need to go from moles to molecules. The conversion factor there is 6.02 times 10 to the 23rd. It's 6.02 times 10 to the 23rd molecules in 1 mole. If we go through here, we've got 4 sig figs in the mass. We've got 5 sig figs in the molar mass conversion factor there, but we've got just 3 sig figs in that 6.02 times 10 to the 23rd. So we have to round our answer to 3 sig figs. That ends up giving us 5.27 times 10 to the 23rd molecules. Of Pi3. All right, question number 3 here, it says what's the volume of 7.9 times 10 to the 24th molecules of carbon dioxide gas. So in this one, we're trying to go to volume, and we are starting with molecules, which is particles. This is again going to require a two-step conversion. We have to go from molecules to moles first, and then from moles to volume. We won't need the molar mass in this case because grams is not involved. There's no mole to gram or gram to mole conversion, so there's no reason to calculate the molar mass in this one. So we start with the number that's given, 7.9 times 10 to the 24th molecules of carbon dioxide, so molecules of CO2. In the first step, we're going to go from molecules of CO2 to moles of CO2. And then in the second step, we're going to go from moles of CO2 to liters of CO2, because that's the volume. All right, conversion factors, going from molecules to moles. In 1 mole, there is 6.02 times 10 to the 23rd molecules. All right, conversion factor, liters in moles, so there's 22.4 liters in 1 mole. 7.9 times 10 to the 24th has 2 significant figures, so that limits our answer to 2 significant figures. If we calculate that, then we get 290 liters of CO2. And then this last one, it says, what is the mass of 4.32 moles of sulfur? So we're going from moles to mass. That is a one-step conversion. So we start with 4.32 moles of sulfur, moles of S. All right. Then we want to get from moles of S to grams of S, because it says what's the mass. To do this, we need the molar mass of sulfur from the periodic table. It is 32.07 grams for 1 mole of sulfur. We should have 3 significant figures on our answer, so it rounds to 139 grams of sulfur. All right, this section B is about percent composition. This is pretty much the same exact process every single time, so if you've got a handle on this, you should be pretty good to go on the exam. The first thing that we do is we find the individual masses of the elements. And so we start, for instance, we say carbon, all right, and there are 6 carbons, so 6 times 12.01, which is the molar mass of carbon from the periodic table. You multiply that out, you get 72.06. Okay, so it's 72.06 grams for carbon. For hydrogen, there's 12 of the hydrogens. Each one has a mass of 1.01. You multiply that all together, and you get 12.12 grams for the total amount of hydrogen in this. And for oxygen, there are 6 of them, and they have a mass of 16.00 each. If we multiply 6 times 16, we get 96.00. The next thing you do is you combine these all together. All right. So just add up the individual masses, and you get a total mass of 180. .18 grams. Next we need to find the percentages of each, and so what we do is we take the mass of the element, we divide it by the total mass, and we multiply by 100, and then we get the percent mass of that element. So for instance, for carbon, we know that we've got 72.06 grams. We divide it by the total, 180.18, and then times 100. And then you get 39.99% carbon. For hydrogen, is 12.12 over 180.18 times 100. And you get 6.73% hydrogen. And then lastly, for the oxygen, 96.00 grams over 180.16 times 100. And you get 53.28. And that is percent oxygen. The last step is add all of these together and make sure that it adds together to something that's like 100%. So if you add these ones together, you should see that it actually equals exactly 100%. It might be off by, a few hundredths of a percent, but it should, generally speaking, add up to be almost exactly 100 every time. All right, on the back here, we're doing empirical formula problems. And so these set up the same way every time, but it's important that you kind of get the process down. So the first thing that you have to do is I just kind of make my table here. I'll underline, actually usually I go above each one of these. So I'll put a mark up here so that I can put the header row in, and mark above here, mark above here. Okay, and so the first thing that I do is I convert these to masses. All right, to convert them to masses, we just assume 100 grams and then just copy the number that's written there right over to the mass column. And so it's 76.4 grams and 5.3 grams and then 18.3 grams. The next step is to get it into moles. We do this by dividing by the molar mass that's on the periodic table. For instance, the molar mass of mercury, that Hg, is 200.59. Okay, so we use that 200.59 in this problem, and we divide 76.4 by 200.59, and you get 0.381. For nitrogen, the molar mass is 14.01. All right, so we take 5.3 and divide it by 14.01, and you get 0.378. And then lastly, oxygen, the mass from the periodic table is 16.00. So you take 18.3 and divide it by 16.00, and you get 1.14. The next step is to find the ratio between these different sides. To do that, you divide by the one that has the smallest number. In this case, it's 0.378. All right, so if you look at the number of moles, we got 0.381, 0.378, and 1.14. 0.378 is the smallest, So we're going to divide each of the numbers in the mole column by 0.378. All right, that one's easy because 0.378 divided by 0.378 is going to give you 1. On the top row, we've got 0.381 divided by 0.378, and we get 1.01. And then on the bottom here, 1.14 divided by 0.378, you get 3.02. All right. Now in the last step, we have to try and find whole numbers that go with these ratios. In this one, it's easy because they all fall right around whole numbers. And so I'm going to assume that this 1.01 is just a 1 with some rounding error, and the 1, of course, is a 1. And then 3.02 is a 3 because of some rounding error. And what we end up with here is 1, 1, and 3. And so the last step of this is to write out the formula. This has 1 mercury, 1 nitrogen, and 3 oxygens. So it has a formula of HgNO3. For number 2, it's the same exact process. So we start here with mass, and then we go to moles, and then we do the ratio, and then we try and find the whole number ratio. To get to mass, again, you just copy the number right over. So we've got 32.7 grams and 38.2 grams and 29.1 grams. Then as a reminder, the way that we get from mass to moles is by dividing by the molar mass of each element. So 32.7 divided by 12.01 is going to give us 2.72. All right. With nitrogen, we're dividing by 14.01. We get 2.73. And then with oxygen, we're dividing by 16, and we get 1.82. For the ratio, then, we divide by the smallest number here. In this case, for the moles, the smallest number is 1.82, so we're dividing each of these by 1.82. That means that this is going to give us a 1 in this row. For the other two rows, I get 1.49 and 1.5. So in this case, when you look at the ratios, you should identify that they're not near whole numbers. All right, in fact, they're near some fractions. They're near 1.5 there for the 1.5s. And so if we want to get these to be whole numbers, identifying that they're related to halves, what we have to do is we have to multiply by 2. All right, so if we multiply each of these by 2, 1.49 becomes something like 3, 1.5 becomes 3, and 1 becomes 2. Right, so anytime you get a fraction in the ratio, a decimal that looks like a recognizable fraction, you need to multiply it by the denominator of whatever that fraction is. All right, so in this case, we were talking about halves. So that means we've got a formula here of C3H3O2. And then the short answer here are already sort of written in, but I'll explain. So it says, if you have 1 mole of marbles and 1 mole of bowling balls, which do you have more of and which would occupy a larger volume? Explain your answers. So in this case, what we're kind of comparing it to is the molar volume of something that's small, like sodium chloride, versus the molar volume of something that is large, like sugar. And so when I brought those baggies into class and you saw that a mole of sodium chloride, a mole of table salt, actually was much, much smaller in volume than a mole of sugar, I indicated that that was because the two different particles had different sizes. A sugar molecule is much, much larger than a formula unit of sodium chloride. And so in the similar way, if you have a mole of something, that means you have 6.02 times 10 to the 23rd. Okay, so if we have a mole of marbles and a mole of bowling balls, we have the same number of marbles and the same number of bowling balls. It's 6.02 times 10 to the 23rd of each of those. All right, and so therefore the basketballs are going to occupy more volume because you have the same number of them and each basketball is larger. Hopefully that makes sense. So you've got the same number of marbles as you have basketballs, and basketballs are larger. Therefore, the basketballs take up more volume. For number 2, it says what needs to be true in order to assume that a mole of a substance occupies a volume of 22.4 liters. So we use this a lot, and I don't really often mention the requirements because we just kind of put it into the problems all the time because I always say assume STP, and I think people have fallen into the habit of just not thinking about it. But I want to remind you that this is only true for gases, and it's only true at standard temperature and pressure. And so if you had a solid, all right, you wouldn't be able to use this 22.4 liters per mole because it wouldn't be a gas. Furthermore, if you had a gas but it wasn't at standard temperature and pressure, it would not work either. And then as a reminder, the standard temperature is 0 degrees Celsius and the standard pressure is 1 atmosphere of pressure. 0 degrees Celsius is the freezing point for water, and 1 atmosphere is the normal atmospheric pressure at sea level. And so if you're, say, standing next to one of the oceans or standing next to the Gulf of Mexico on an average day, the air pressure on that day is 1 atmosphere of pressure, and that is the standard pressure that we use in chemistry. Working through these problems should have given you a pretty good idea of what's going to be on the test. If you have any questions over any of these, make sure that you come in and ask. Take special care on the mole conversion problems from page 1 that you are checking the sig figs and making sure that not only that you get the right answer numerically speaking, but that also you get the correct number of sig figs, that it's rounded correctly, and that it has the right label, because all of those things are things that I'll be grading you on.